So 30 minutes, I think you would like me to speak. Yes, about that, right. So, next semester I'll be teaching my regular Stage 3 course on the history of mathematics. And one of the remarkable features of the history of mathematics is how ideas might be developed intensely for a period and then go out of fashion. For example, at secondary school level, geometry disappeared from the curriculum in the 1960s, and nothing has been found to replace it as yet. But many ideas which had gone out of fashion have later been revived because they have been found to be practically useful. And geometry is a good case in point. One of the earliest centres of civilization was in Egypt. And in Egypt, from Egypt, two mathematical books have survived, written one about the minus 18th century, the other about the minus 16th century. They're scrolls of papyrus, each a bit over 5 meters long, one of them is 8 centimeters wide, the other 32 centimeters wide. And both of those papyrus books are collections of problems with solutions. No proofs are found in them. And one of the most remarkable achievements in the older of the papyri, the Moscow papyrus, because it's held in the museum in Moscow, is a simple and remarkably accurate formula for the volume of a cylinder. The rule is from the diameter of the circle, take away 1/9, multiply what is left, and that gives a good approximation to the area of the circle. The area is about 0.6%. And then that area of the circle, multiply it by the height. A simple rule, very easy to work out and accurate enough for many practical purposes. I found a practical purpose. Auckland University Underwater Club this year is celebrating its 50th anniversary. In 1969, I joined it, and after the very good training course, we went for 4 days and a night diving at the Poor Knights Islands. And remarkably, on our 3rd day there, we met up with the sunfish in a friendly mood. So, sunfish are very timid. Ordinarily, if anyone comes near a sunfish, swimming or by boat, will dive down. But we were so fortunate as to meet up with one in a friendly mood. And there were 2 graduate students of marine biology, Roger Grace and Tony Ayling, both of whom quickly became eminent marine biologists, which they remain to this day. So Tony chased the sunfish, grabbed hold of it, tried to shake him off, but as a true scientist, he was collecting parasites from the hide of the sunfish, putting them in these specimen bottles. The sunfish liked having its back scratched, and so it calmed down and invited us to play with it. This was in May 1969, when there were very few underwater cameras in New Zealand, and most of them were focused on the sunfish that day. So you can get some idea of the size of the sunfish from the diver here and another view. So while I was playing with that sunfish, I thought, well, I could work out its volume, and from the volume I can get its weight, because fish use their swim bladder to maintain neutral buoyancy. So to a good approximation, I approximated by a cylinder 2.7 meters diameter and averaging about 0.15 meters thick. So take away the Egyptian rule, take away 1/9 of the diameter, get 2.4, square that 5.76, multiply that by 1.5, get 862, I think, 0.862 of a cubic meter. seawater is a few percent denser than fresh water. Fresh water weighs 1,000 kilograms per cubic metre, seawater a few percent more, and so while playing with that friendly sunfish, I estimated its weight as about 880 kilograms. I was able to check that later. Both Auckland Museum and Otago Museum have plaster casts of similar sized sunfish which have been washed up on beaches, and from the stated weights of those museum casts I saw that the weight which I'd estimated by the ancient Egyptian formula was quite accurate. Now, in ancient Greek mathematics, the subject of conic sections was highly developed. It grew out of an event when one city was subject to plague, and so the city paid for a consultation by the oracle at Delphi, and the oracle declared that the god Zeus was dissatisfied with the size of his altar in the temple. It was a cube, and Zeus would remove the plague, so the legend went, if the size of the altar was doubled, and that was interpreted by ancient Greece as meaning doubling the volume of a cube. So without going into the mathematical details, although geometry with ruler, with straight edge and compass was well developed by that time, that wasn't found to be a practical way of doubling the volume of a cube. You have to multiply the side of a cube by the cube root of 2. And only in about 1860 was mathematics advanced to the level to prove that straight edge and compass weren't enough to do that. So Menaechmus considered sections of a cone by a plane, and there are three types: the ellipse, the parabola, and hyperbola. Those names were given later by Archimedes. So this is the ellipse with a circle as a special case. The hyperbola, a curve with two branches, and in between them the parabola. Right. So the mathematics of those was highly developed by ancient Greek mathematicians, particularly Archimedes in the mind's 3rd century. And about 100 years after the lifetime of Archimedes, Diocles showed that if you make a mirror whose section is a parabola and rotate it about an axis, then any light coming, say, from the sun, which is parallel to the axis, will get reflected so that all the light passes through the focus of the parabola. And his book on the subject was entitled Burning Mirrors, and it appears probable that some attempts, burning mirrors round out of bronze and sometimes iron were extensively used in ancient Greece and Rome, and some attempts were made to grind these mirrors so they did have a parabolic section, but with limited success. It was Isaac Newton in 1670 who made a parabolic mirror good enough to make the first practical telescope. So, but about 55 years before Newton made a workable parabolic mirror, Kepler, trying to produce accurate predictions of the planetary motions, well, he abandoned the Earth-centered geometry, which had been traditional, accepted Copernicus's idea of a sun-centered astronomy, but Copernicus still followed the tradition that all astronomical bodies must move in circles, with smaller circles on them and smaller circles on those, etc. And Kepler in 1609 published his astonishing discovery that instead each planet moves in an elliptical orbit with the sun the centre of the focus. And so for 2,000 years after Menaechmus had invented the conic sections, reputedly to satisfy the oracle's order for the altar of Zeus, they were found to be of great importance in science, and a few decades later Newton very greatly advanced optics and astronomy by successfully making mirrors of parabolic form. Right. Quadratic equations have been solved for about 4,000 years, starting in ancient Mesopotamia. And then they were widely solved in other early cultures, India, China, etc. But nowhere do we find any indication of complex numbers. Consider the quadratic equation x squared plus 1 equals 0. Until the 15th century, late 15th, early 16th century, when several Italian astronomers, mathematicians rather, managed to get algebraic solutions to cubic equations and quartic, that is polynomial equations of degree 4. But there was an awkward factor. If the cubic had one real root, the algebraic method worked nicely. But if it had 3 real roots, each of those was expressed by complex numbers involving square roots of negative numbers. And so for centuries there was much muddle and confusion. Complex numbers were used to find many remarkable results in mathematics, but a great deal of nonsense as well. And it was not until 1831 that the Irish mathematician William Rowan Hamilton gave the first definition of complex numbers, which was clear enough to be immediately usable on computers once the first computers were built 180 years later. And so the complex number in Newton was a plus ib. He defined it as an ordered pair of real numbers and defined equality, addition, subtraction, multiplication, division, and showed those pairs of numbers obeyed all of the ordinary rules of algebra. And so Hamilton then tried to extend that from pairs of numbers to triples. For 13 years he made many attempts, and so did several of his friends, but none of them produced any sensible result. They just couldn't carry over the ordinary rules of arithmetic and algebra to triples. But then in 1843, whilst Hamilton was walking over Broome Bridge, he was Astronomer Royal of Ireland, living at Dunsink Observatory outside Dublin. He was walking over the bridge to get to the Royal Irish Academy, which he was president, and he realised in a flash of insight that he could get useful results. He considered sets of 4 numbers, not 3, provided he was willing, and he called those quaternions, and he realised that they obeyed almost all of these ordinary rules of arithmetic and algebra, except that x times y is not, in general not equal to y times x. That one exception, all of the conventional rules used in arithmetic and algebra could be applied. It was 1843. Quaternions became a subject of intense interest worldwide. Within a few years after the invention, they were being earnestly debated in the University of Kazan on the Volga, 700 kilometers east of Moscow. In 1878, when Sir George Grey, at the age of 62, was Premier of New Zealand, he was intensely studying quaternions. Grey had a very strong interest in science, particularly mathematics. Within a few years, Hobart became a significant centre for research in quaternions. But within the period of about 1900 to 1906, quaternions very abruptly went out of fashion. An English engineer and an American physicist had each thought the mathematics of quaternions, with its awkward rule about multiplication, was too complicated, so they produced a stripped-down version, so some regard as a crippled version. And those of you who have studied vector calculus and dot products and cross products will know that nobody could describe the mathematics of vector calculus as elegant or convenient. But it was simpler. So quaternions dropped completely out of fashion. However, computers came into use, and quaternions could easily be handled on those. And so during the past 20 years, there's been great resurgence of interest in quaternions, not only amongst mathematicians who now seem to use them, but engineers, particularly mechanical engineers and those concerned with robotic machinery, computer scientists, particularly those concerned with computer graphics, make extensive use of quaternions. And some of the 19th century books on quaternions have been reprinted in recent years because of the growing demand for that subject. So, linear systems of linear equations, the study of those was highly developed in China by about the -2nd century. They got very close to modern matrix representations of systems of linear equation and their solution. And then in Japan, in about 1670, the mathematician Seki Takakazu invented the determinant. So in modern terms, you have a square matrix. Yes. For a square matrix, there's complicated rules for calculating a single number from the elements in those matrices. 10 years, about 1693 in Germany, Leibniz independently invented them. And they were developed enormously. Our library has 5 fat volumes by Thomas Muir dealing with the history of determinants from 1690 until 1920. In 1858, the English mathematician Cayley returned essentially to the ancient Chinese representation of equations and invented the matrix. So instead of boiling down the square determinant to a single number, you keep a rectangular array of the numbers, and he points out they don't need to be square. It's of interest to consider rectangular matrices with different numbers of rows and columns. And Cayley was a very famous mathematician at that time, but the physicist William Thomson, later Lord Kelvin, in a letter to the German physicist Kirchhoff, who solved a very knotty problem in elasticity theory. Kelvin expresses exasperation that Cayley, instead of applying his great talents to the subject of really difficult problems, which is the one Kirchhoff had solved, fritters away his time on matrices which are of interest to himself and at most 4 or 5 other people, if any. So, matrices failed to attract much attention. Until 1925, physicists were trying to cope with the quantum aspects of physics, particularly the relations between atoms and light. And they were groping around in the dark, making guesses, and some of the guesses, such as Bohr's theory of the atom, of the hydrogen atom, proved spectacularly successful for calculating the details of the light emitted by hydrogen atoms. But all of these are just guesses and arbitrary rules. So there was, at Göttingen University, there was a student in short pants. Well, in Germany, that doesn't have quite the same meaning as it does in New Zealand. This was a graduate student, Werner Heisenberg. And he tried drawing up rectangular tables of numbers related to atoms and light, and then defining operations on those. It was easy enough to add 2 such tables together and subtract them if they had the same number of rows and columns. He devised a very strange looking rule for multiplying together 2 such shopping lists, as he called them. But then his supervisor, the very eminent physicist Max Born, looked over the graduate student's shoulder and said, "But those are matrices." And so, since 1858, when Cayley published ideas, they'd been almost totally ignored, but Max Born knew of them. And within a year, physicists around the world were wildly excited because the matrix mechanics of Heisenberg proved to be a very useful way of dealing with the interactions between light and matter. And then within a few years, engineers, particularly those in civil engineering and aeronautical engineering, were trying to deal with vibrations of structures, and matrices were found to be very useful for those. So, in 1851, before matrices had been invented, when people were still thinking in terms of determinants, Spottiswoode, a reputable but not widely known mathematician of that period, proved a theorem which he described as curious but not important. No, sorry, that was Muir in his 5-volume history, described Spottiswoode's theorem as curious but not important. That unimportant theorem, if we express it in terms of matrices, if we have AX equals 0, where A is a square matrix, we have a column of zeros here. Spottiswoode proved that a vector x, which is not equal to the 0 matrix, can exist if and only if the determinant of A is equal to 0. So, by about the time of Heisenberg, it was realized that Spottiswoode's uninteresting theorem was exactly what was needed for dealing with the very difficult problem of vibrations of structures. And so the first textbook of matrices was written in about 1938 by 3 engineers in England. and they demonstrated how very useful matrices are in many problems in physics and in engineering. So the first computer was built in 1943, the now famous Colossus at Bletchley Park, which was kept totally secret for 40 years. 30 years. And those few people who had access to the few early computers quickly realized that matrices were very convenient things to handle on computer. And you get very neat, compact operation. And so, matrix theory was very greatly advanced. The best quality of mathematics, mathematical software, had a great many programs for matrix algebra, particularly NAG, which is at the mathematical heart of Maple and other of the better quality mathematical software systems. Matrix theory was greatly developed. So when I was a student here from 1949 to 1954, matrices were very briefly mentioned in mathematics at stage 2 level and somewhat more fully in physics at stage 3. But by about 1960, the better quality textbooks of algebra gave strong emphasis to matrices, and they became widely taught at secondary school level.
I'm sure there are some people here who don't know much about mathematics. Could you just give a very brief overview of what a matrix is for those who might only be familiar with the film?
So if we consider a set of equations such as 2x1 minus 3x2 equals 5, 4x1 plus x2 plus 2x3 equals minus 2, and let's say 5x2 minus 3x3 equals 4. That can very conveniently be written in terms of the matrices. We have A as these coefficients here, 2 minus 3, 0, 4, 1, 2, 0, 5, minus 3. And if we have called B, the matrix, there's one column here, 5 minus 2, 4, and the solution X consists of here x1, x2, x3. Then, in matrix notation, that is AX equals B. And ancient Chinese mathematicians developed very efficient ways of operating on these matrices to produce the solution to the equation. So is that sufficient at this stage?
Yeah. Could you just move it so you can see that?
Right, so I have to skip there. So, from Spottiswood's work, we found that if we have problems along AV equals V lambda, as we want a vector V, so we multiply it by a matrix, we get the original vector V back times lambda. So Spottiswood's theorem is very useful in dealing with that. And vibration problems and many problems in physics and engineering involved these vectors V, which we call eigenvectors, and these numbers called eigenvalues. So from the 1920s onwards, those became of intense interest to physicists and engineers, and they're enormously useful in many fields. And a rather unexpected consequence of that. Early versions of the internet were developed in the late 1970s. By the early 1980s, quite a lot of material was available through the early versions of the internet, although imperceptible compared with the torrents of information and misinformation on the internet these days. So by the early 1980s, some of the few people with access to early versions of the internet tried to develop software to aid people searching to find material in the internet. So only a limited amount of information was available. Those early versions of search engines required very lengthy computation. A friend of mine, Jean Golub, at the University of Stanford University, who died a couple of years ago, was a leading researcher on eigenvectors. And he was dissatisfied with the very slow operation of the early search engines. And so Jean Golub applied his very great expertise in eigenvectors to show how to design search engines which were very, very much faster than anything previously. And search engines took off explosively from them. Google and various other search engines are all based on Jean Golub's use of eigenvectors to show efficient ways of searching the internet. So Jean received many scientific prizes and honours during his life, including some industrial prizes, and the Google Limited backed that up with a large portfolio of shares in their company, which they presented to the mathematician. Jean then sold those shares, but then he gave the money to the University of Chicago for a chair in computer science in honor of two of his teachers at the University of Chicago. So whenever you go searching on the internet, you should spare a thought for the mathematician Jean Golub, whose very great skills in eigenvectors made search engines such as Google as efficient and powerful as they are today. So I've got a few papers here for you which you might like to read. The first is a lecture which I gave in London about mathematics in the Pacific Basin. This was as part of the celebrations of the 200th anniversary of the English dumping many of their convicts at Botany Bay. And so I speak mostly about mathematics in New Zealand and Australia, but also in other parts of the Pacific. This article with photographs of the sunfish by Roger Grace was published in the Auckland weekly magazine Weekly News, and that was here. And for my course on the history of mathematics, there's a handout for the section on the history of numbers, which does include a brief account of the simple ancient Egyptian method for the volume of a cylinder, and a handout for the part of my course dealing with the origins of calculus.